Alright, so here we are looking at part 2 of the week 7 RScript. And for this part of the tutorials, I'm just going to walk you through the binomial test. So remember this binomial test, this is following example 7.2 from your textbook. And of course I'm paraphrasing here a little bit, but just to get you caught up to speed if you don't happen to be looking at your textbook right now. This example involved a study of 25 spermatogenesis genes, and these spermatogenesis genes are found in the mouse genome. And the researchers did a study to test whether or not the genes occurred disproportionately on the X chromosome. So they found 10 out of the 25 genes, which is 40% of the genes on the X chromosome. However, in formulating the null hypothesis, because the X chromosome holds 6.1% of the genes in the genome, the null hypothesis, if the genes occur randomly, is that 6.1% of spermatogenesis genes would be found on the X chromosome. So, binomially speaking, what this means is that the probability of success being on the X chromosome is 0.061. So this is our null hypothesis for this experiment. So if this is the null hypothesis, that means that our alternate hypothesis is that the probability of success is something other than 0.061. So there are two ways to do this. You could have values on either side, so on either tail of the distribution. They could be greater than or equal to, or they could be less than or equal to. So basically anything other than 0.061. All right, so here the test statistic for a binomial test is the observed number of successes. And here the observed number of successes is 10, because remember we classified success as being on the X chromosome. So, as I said before, you've already really done these binomial tests. You just didn't get to the last part, which is figuring out what exactly the p-value for your test would be, because we hadn't yet talked about formulating hypotheses. So, the null expectation here is that 6.1% or 0.061 proportion times 25 spermatogenesis genes is equal to 1.525 genes on the X chromosome on average. So this is how many that we would expect to find on the X chromosome if the null hypothesis is true. Now, remember, we use the binomial distribution to determine probabilities of getting X numbers of successes out of n trials, given p as the probability of success. So, if we want to know the probability of getting exactly 10 out of 25 genes on the X chromosome, then the probability of being on the X chromosome is 0.061, and that's going to be given by this formula, d binom, 10 because 10 successes, 25, that's the number of events, the number of spermatogenesis genes, and then the probability of success, 0.061. Now, to calculate the probability of 10 or more spermatogenesis genes on the X chromosome, assuming that the null hypothesis is true, this is simply going to be the sum of all of the mutually exclusive probabilities. So you could calculate this probability for each number, starting with 10 and working up to 25. Okay, but imagine how much work that would be. Here we could go ahead and assign p a value of 0.061, assign n a value of 25, and if we do actually write all of this out, we see that this is the number we come up with. Okay. Now, instead of writing all this out each time, we could just use the cumulative probability function. So, by itself, p binom here is what we want to be looking at rather than d binom. So with p binom, this is the cumulative probability of less than or equal to the number that you have entered for x, your number of successes. And this is because, as a default, R uses lower dot tail equal true by default. So, because this is default, this means that you don't have to specify this, But if it makes it easier for you to remember where you need to specify this, you can go ahead and just put lower.tail equals true at all times unless you are trying to reverse it. If you are trying to reverse things and the value that you want is the probability of having greater than some number, then you have to enter lower.tail equal to false. Alright, so that being said, there are many different ways that you can actually get at this question. Okay, so here, one way to do this is simply 1 minus the probability of 9 or fewer. Okay, that's one way to get the answer here. Notice if we enter the line of code like this, where we are specifying lower tail equal to true, we get exactly the same value. And this is because lower.tail equal to true is the default value. So even though we're not telling it up here in this line, it's doing the same thing. Okay. We could also take advantage of the sum feature. So here we're doing sum of all of the D binomes from 10 to 25. Okay, so this is very similar to what we did above right here, where we actually typed each and every one out. And we can also do it like this. Okay? And I ask you to think for a moment about why this actually works. And the reason that this works is that the cumulative probability of getting 25 successes out of 25 total opportunities is going to be 1. So this is the same as the very first entry that we made up here. Okay, so in thinking about why it is that this works, okay, and we could actually even call this up just to prove to ourselves, in fact, that we do get 1. So that's why that works. All right, so what is the final p-value, though? In order to figure out the final p-value, and this is why we didn't talk about this before when we were looking at binomial distributions, we have to think about 1 and 2 sample tests. And remember that most of the tests that you do are going to be two-tail tests. And in this example, we were curious about the cases where we had as extreme as or greater than, so 10 or greater, or we could be extreme at the opposite end, so on the other tail of the distribution. So this means that this is a two-tail test that we're doing here. So to get the p-value, all we have to do is multiply the probability that we've already calculated by 2. So this will tell us what our p-value for the binomial test is. Okay? So how does this actually work? Well, this is the p-value for the binomial test, and at 1.99 times 10 to the negative 6, it's well below the typical significance level, or alpha, of 0.05. So we can reject the null hypothesis, and we can say that there is in fact a disproportionate number of spermatogenesis genes on the X chromosome. And we can say this because we calculated the probability of getting a result as extreme or more extreme than what was observed, 10, if the null hypothesis were true. And this value here for p is far less than our significance level of 0.05. Therefore, we reject the null hypothesis and we accept the alternate hypothesis that this value is something other than 0.061. All right, so this sums it up for part 2 of the week 7 script. Tune in for part 3 when I will go through chi-square contingency tests, also known as tests of independence in R.